Task number 6, NAT. As discussed in the networking concepts room, we calculated that IPv4 can support a maximum of 4 billion devices. With the increase in the number of devices connected to the internet, from computers and smartphones to security cameras and washing machines, it was clear that the IPv4 addresses would be depleted quickly. One solution to address depletion is network address translation, NAT. The idea behind NAT lies in using one public IP address to provide internet across the many private IP addresses. In other words, if you are connecting a company with 20 computers, you can provide internet access to all 20 computers by using a single public IP address instead of 20 public IP addresses. Note, technically speaking, the number of IP addresses is always expressed as a power of 2. To be technically accurate, with NAT, you reserve 2 public IP addresses instead of 32. Consequently, you would have saved 30 public IP addresses. Unlike routing, which is the natural way to route packets to the destination host, routers that support NAT must find a way to track ongoing connections. Consequently, NAT supporting routers maintain a table translating network addresses between internal and external networks. Generally, the internal network would use a private IP address range, while the external network would use a public IP address. In the diagram below, multiple devices access the internet via a router that supports NAT. The router maintains a table that maps the internal IP address and port number with its external IP address and port number. For instance, the laptop might establish a connection with some web server. From the laptop perspective, the connection is initiated from its IP address. The following from TCP source port number, this one. However, the web server will see this same connection as being established from this and TCP port this, as shown in the translation table. The router does this address translation seamlessly. Yes, so this is the router, this is the internet, and these are our addresses, devices. Also, yes, their addresses respectively. So we have internal network for all of these, and we have external network for this. What happens after the router? So between the router and the internet, everything is external. But what happens here to all the devices and the router is internal. Answer the questions below. In the network diagram above, what is the public IP that the phone will appear to use when accessing the internet? This is the public IP address. So it's 212.345. Assuming that the router has infinite processing power, approximately speaking, how many thousand simultaneous TCP connections can it maintain? Why 65? I just realized I filmed a video and I read everything with my mind. So there are 65,535 available TCP ports. This is why the answer to the question is 65. Number from 0 to 65,535, because TCP port number are 16-bit unsigned integers, allowing 2 to the power of 16 possible values. So there is your answer. And then if we say UDP, we will find the same absolute answer, right? Because these two can be used for, basically they are two protocols used by the transport layer in the OSI and TCP IP models.